Hello, welcome to the presentation of our CVPR 2024 paper, titled Robust Self-calibration of Focal Lengths from the Fundamental Matrix. Our paper deals with camera calibration, which is a crucial component in many 3D vision applications. The camera calibration process involves the estimation of camera intrinsics, like the focal length and the principal point. This can be done offline, usually by using images of calibration patterns. However, such offline calibration is not always possible. In many applications, we need to calibrate our cameras online using general images. This process is known as self-calibration. In this process, we estimate the intrinsic camera parameters. For many cameras, it is possible to use some reliable assumptions for most intrinsics and have the focal length the only unknown intrinsic parameter. In the general case, at least 2 images of the same scene are required. The 2 images can also be captured by 2 cameras with different focal lengths. Their geometry is described by the fundamental matrix, which contains the information about the camera intrinsics as well as the relative pose of the 2 cameras. The fundamental matrix can be estimated using point correspondences between the 2 images inside a robust estimation framework, like RONSAC. After the fundamental matrix is estimated, it is possible to extract the focal lengths of both cameras in closed form using the Voinau formula. Unfortunately, this approach has 2 main limitations. The formula has a singularity when the principal axes of the 2 cameras intersect or are parallel. This degenerate configuration occurs quite often in practice, as photographers usually place objects of interest in the centers of images. This leads to unstable results in many common scenarios. Moreover, the focal lengths are estimated in their squared form, and thus often lead to physically impossible imaginary focal lengths due to instability or noise. An alternative approach is to use iterative optimization to optimize for a multi-term loss, which assumes user-defined priors on the focal lengths and principal point positions. This approach can compensate for the errors in the assumed principal point position and errors in the fundamental matrix, but it suffers from the same singularities as the Voinau formula that is used within the iterations. Moreover, the method requires expensive computations and requires many iterations to converge, making the method slow in practice. In our paper, we propose a new method for camera self-calibration, which we formulate as an optimization problem using a simpler loss function. We solve the optimization problem using an efficient iterative algorithm. Our method provides more accurate results than all state-of-the-art approaches, while being faster than other iterative approaches. We also propose a new check within RONSAC to reject bad models, leading to further improvement in terms of accuracy and speed. We extensively tested the proposed methods on real-world datasets using different features, matchers, and RONSAC variants. We formulate the problem as constrained optimization. We minimize the distance of the estimated focal lengths and principal points to user-defined priors under the constraint that the Krupa equations hold. To solve the problem, we use the Lagrangian, which yields a system of polynomial equations. However, finding its roots using algebraic methods is not feasible. Instead, we propose a hybrid iterative and algebraic approach, where we fix the unknowns in higher-order polynomials to values estimated in the previous iteration step. In each iteration, we solve 2 polynomial equations of degree 4 using a Grobner basis solver. The proposed method usually converges in less than 50 iterations. Synthetic experiments show that our method in blue outperforms the baselines when the camera configuration is close to degenerate. Our method requires prior estimates for the focal length. However, we show in synthetic experiments that even for inaccurate priors, our method performs well. Our second contribution, real focal length checking, is based on the observation that the fundamental matrices, which led to imaginary focal lengths when using the Voinau formula, usually lead to fewer inliers than models leading to real focal lengths. We use this along with an efficient variant of the Voinau formula to reject such models inside RONSAC. This leads to faster RONSAC times since fewer bad models have to be scored. Our method also results in better accuracy of the estimated fundamental matrices. We evaluate both of our contributions on 2 large publicly available datasets, Phototourism and Aucun Night. To set the priors for focal lengths, we use a heuristic, which is equivalent to assuming that the cameras have roughly a 50 degrees field of view. Our results show that our iterative method outperforms the state-of-the-art in terms of the estimated focal lengths. The results also show that the proposed real focal length checking results in further improvement for all the methods tested. The results shown are for the fundamental matrix estimated using MagZac++ and LOFTR matches. We also show similar improvement in terms of the accuracy of the computed relative poses. Further experiments providing similar results for other RONSAC variants and matches are provided in the paper. To conclude, our method for focal length estimation from the fundamental matrix outperforms state-of-the-art methods in terms of accuracy and is faster than previous iterative approaches. If you need to use images with unknown intrinsics, such as crowdsourced images, or images captured with a single camera with changing focal length, consider using our method. Our second contribution, RFC, can be used whenever the fundamental matrix is estimated using RONSAC, leading to faster and more accurate results. You can also find more information in our paper. The code is available on GitHub. Thank you for your attention.